interesting to you for some time in your life if you decide to engage them. I think you might enjoy it a lot. So that was fun with the animals. Let's do a little more on algorithm design to kind of round out our course, and then I'll make some comments at the end. And I'll have office hours afterwards if anyone wants to chat. Okay, let me share my screen and we'll do some more work on algorithms design. Where were we before? Let me go over there with you. So this is a little summary of what I wanted to remind you of where we were and do some more. So we started out talking about a purely mathematical question, the question of convexity. And essentially, how can clever algorithms exploit this notion to do useful things efficiently? And we talked about well-formed polygons. These are polygons where the vertices cycle around in a particular order. Not well-formed polygons are these monstrosities over here. And we came up with some pretty cool algorithms. So for example, we talked about convex hull. Remember, you could think of the convex hull as being what happens when you have a bunch of points in the plane and you have your friend George the geometry sheep, another kind of pet, helps you find the convex hull by stretching a rubber band around them, the smallest or minimal convex polygon containing all of the points. You might hope to do that efficiently, and we came up with a bunch of algorithms, and you read about them too probably. For example, gift wrapping in order n squared time, divide and conquer, and gram scan, both n log n. They work in different kinds of dimensions, and we investigated that a little bit. And today I'd like to finish answering our question about lower bounds, namely how fast can you do this? Like, could we get convex hull even faster? And talk about how is convex hull actually used in computer science and applications in robotics, graphics, data science, and so forth. Talk a little more about robotics, which generally is popular. So I know from talking with a few of you out of band, some of you have been very assiduous about trying some of these problems, that actually there are some ideas on my question, which is, hey, we can do convex hull really quickly in all these ways. And in fact, the fact that I could have this algorithm that appears to mechanically compute this almost instantaneously, could you actually be very clever and get an algorithm down to optimal, which would be in fact linear time? Is that actually possible in this case? So I'd like to open up the floor and ask if anyone, especially someone who thought about this problem, maybe even who talked to me, could give me an idea of my question. Is there a lower bound? In other words, can you either come up with an algorithm that would be linear time, or can you show that a linear time algorithm is unlikely to exist? Any thoughts on that? Would you like to jump in here and tell me? So important question, because then we know we're done. If we have the optimal algorithm, we can, at that point we can go out for coffee and call it a day. But if we don't know, we might work very hard. So who thought about this problem and would like to venture an idea about how we might get at it?
Okay, I guess I can take a shot. So like, basically the idea is I think you have to reduce this to a sort, because we can kind of have some intuition that when we have a convex hull created, it clearly has to sort the elements in some kind of order, because otherwise you have a really weird pattern where you have like lines going across the convex hull. So it has to clearly sort. And right now our best sort is n log n time. And so if we reduce this to a sorting problem, then you're essentially saying, hey, I haven't come up with a better sort than n log n time, but neither have like everyone else in the history of computer science who's tried it. Therefore, like unless you like have groundbreaking discoveries in the field of sorting that let you sort in like ON time, then you're done.
Yeah, I think that's definitely in the right direction. And I believe that Paul also came up with a similar way of approaching this. I believe that the one thing I would say is that your description is good, but I think you have the reduction going the wrong way. Is that instead of reducing this problem to sort, you want to reduce sorting to convex hull. Does that make sense?
So essentially say that, sorry, could you explain just a little bit more what exactly the distinction is?
Well, so it's the direction of the reduction. So you're turning an instance of sort into an instance of convex hull, or you're turning an instance of convex hull into an instance of sort. So when you said you wanted to reduce this problem to sort, that means you're going to take an instance of sort. I mean, the reduction typically goes in the wrong direction, right? When you think of it that way. So we want to turn an instance of sort into an instance of convex hull. Perhaps I can write that down to give an idea. But I think it's just really just a language thing. But this is the thing that will be trickiest for you in general, is getting the direction of the reduction to be correct. You want to reduce sort of the putative harder problem to the easier problem. So yeah, let me answer your question. And Paul, I know you had this too, so feel free to jump in at any time if you want. Let's kind of see how we could do this. So let's think about this. So what we want to do here is we want to build a reduction pipeline as we had before. So I want to take a list of numbers, and I want to put them into a reducer function. This is just a scheme function. And this is going to output a set of points P.
I think you stopped sharing the.
Oh, that's not good. Yeah. Thank you. Let's fix that. Yeah. I mean, everything I said was good. So thank you. I don't know how that happened. Maybe it's because I wanted to see Vanille. There we go. All right. So we have a list of numbers. This is what I drew here. So this is the same as we had before. The reduction pipeline goes like this. We take a list of numbers like this. We're going to put that to some reducer function, which is written in scheme. And we get out P, which is a set of points, PTS, in R2. And then we feed this into a convex hull algorithm of some kind like this, right? And then we get out the convex hull of P. Right, so that's really what we're going to do. So obviously, this is an instance of the sort question. And this is an instance of the convex hull problem, right? That's how we're going to think about it. So this is the same precise framework that we had before. I'm just going to turn off sharing for a second so I can spotlight myself, which will make the video a little easier for people to read that are asynchronous. And then we'll come back to sharing. So basically, this is the pipeline we're going to have. So it's exactly the same kind of pipeline we had when we did Turing reductions, and also when we sketched polynomial time reductions. But the thing is that we want these reductions to be even stronger. So if they're just Turing computable, that doesn't really give us any kind of argument. In fact, even if this reducer is only polynomial time, that's not quite what we want either. We actually would like to have this be super efficient. We want this to be linear time. So if there are n numbers, we want this to run in order n time, right? And so that the argument will be that if putatively the convex hull algorithm runs faster, like order n time, I'll put a question mark and a star there, then obviously running two consecutive linear time algorithms is only going to be linear time. But the question is, how can we make this thing actually sort? You know, how do we actually do this? And what can we conclude from this? So I'm going to do a little exercise now, and you can participate in the exercise by either shouting out your answer or by saying it in the chat, assuming I can see it. So I'm going to ask you to give me numbers, and I'm going to sort them using this machine here. So what I want you to do is to make this simple. I'd like you to shout out a few integers that are between 0 and 62 inclusive. And I'll write them down here and then we'll sort them. So can you please get, and there's no tricks here, just shout out some numbers here and I'll put in no particular order.
24.
Good. How about some more?
33.
Good.
5.
5, good.
230.
51.
31, 30, good. What else?
11.
11, a couple more.
8.
Did I hear 8?
Yeah.
All right, what, how about 2 more?
17.
17, one more.
62.
62, all right, at the end, okay. So these are my list of numbers. So what I'm gonna do is I'm gonna take these numbers, which I'll call X, and I'm just gonna, if I call these X, and I'm just gonna map these to X over 10 and interpret it as radians, right, around this. And I'm gonna put these points on the circle, treat these as theta. I'm gonna treat this as a theta angle. So now what I'm gonna do is I'm gonna imagine I have a circle like this, a unit circle, right? Because I don't delete any points, and I'm just going to try to put these on. So let's just remember our radians here, right? So remember, pi over 2, this is about, 1.57, and pi, of course, is 3.14, and then roughly 3 pi over 2 is roughly 4.71, and of course, this is either 0 or it's 2 pi, roughly 6.28, which is why I said 6.2. So this is roughly what these values are in terms of radians. And now I'm just going to take these and I'm going to stick them on the circle, right? So 2.4 is going to be maybe, I don't know, here, right? Point like that. And 3.3 is going to be maybe here, and 3.1 is here. 5 is going to be, let's see, 1/2 is going to be sort of like here. 8 is going to be like there. Right, so we can label these things, right? So that's 24, 31. This is 33, this is 5, this is 8. 11 will be up here like this. And 62 will be over here like this. I may have left out 1 or 2, but yeah, get the basic idea. So what I do is I use the X over 10 value as a theta value like this. And I just stick all these on the circle. So the set of points doesn't include the circle, it just includes these set of points here. So this is my set of points P. I just feed this set of points here into my convex hull algorithm, right? And the convex hull algorithm always produces a well-formed polygon. So it produces a polygon with these points in order like this, obviously cutting some corners like that. That's what it looks like. And then I just read them off in order to sort. So my reduction, and of course you can just do this with trigonometric functions and scheme, is I take in the numbers, I normalize them between 0 and 2 pi. In this case, it was easy because I asked you for special numbers. I produce a list of points that are guaranteed to be on the circle by taking theta, and each of these points has the form cos theta, sine theta. So I stick these guys on the circle then, I feed them in the convex hull algorithm. So this shows that, you can reduce, sorting to convex hull, right? That's pretty interesting. You can use a convex hull algorithm to sort. We still haven't quite guaranteed that, this is difficult or something, right? We haven't done that part of the argument. So let me ask you a question. Do you believe what I've done here? Have I shown that if you have a convex hull algorithm, then if I had a list of numbers, I could use your convex hull algorithm to sort, and I only have to pay a penalty, linear penalty for processing? So here's, Tommy asks, how do you do this? So this is my number. Take a number like 333, right? So I'm gonna assume without loss of generality that I can just scale these. So I'm gonna take 33 and first I'm gonna convert it to 3.3 because I want all my numbers between 0 and 2 pi. So this is now equal to theta. I turn each theta into a point cosine theta and sine theta. That's how you put them on the circle. Tommy, are you happy with that answer? So it's a map, right? I'm mapping a function over the theta values, and for each theta value it produces a pair like this, or a list like this. So this is clearly a map that we could write. So this shows that we can use convex hull to sort, right? And it says that in order to use convex hull to sort, the pre-processing or reduction in some sense only takes linear time, right? So we can do that super quickly in this sense. So how does that help us understand if we're done, if this is optimal? It sort of suggested, and of course, Vanille gave a very articulate argument about why this would be in terms of the hardness of sorting and so forth, which is a great point. So let me just let you think about that for a minute, and then I will come back and ask your opinions. Okay, so what I really want to know is, does this make sense to you all? Is it a reasonable construction? Did I do okay? How do we go on to make the argument that we really probably can't do much better than linear time? And this is where I'm going to try to take the argument that Neil made earlier. And to do this, I think that what I'm going to argue here is that what I've done here said that you can't do convex hull faster than you can sort, right? I can, because I've transformed any sorting problem to convex hull problem, you know, it's not going to be any quicker than that. So if you believe that your fastest sorting algorithms were n log n, then we'd be done. But how do we know this? Well, I gave you a handout on this, but that's just, you know, something you have to read. So I'm going to sort of state it this way. So we're going to have a theorem that I'll let you think about. And where would you understand this theorem to be? So this is a theorem you will prove in CS 330. And I also gave you a handout on the web, right? And basically what this says is what we want to do in this case is we want to say that to sort n objects using comparisons requires n log n time. So there are 3 proofs of this on the web. So if we believe this theorem, and we believe the reduction that Vanille and Paul set up, then we can conclude as a corollary that to compute convex hull of P, where P is in the plane, and P is discrete, and it has n points, requires time n log n. And again, let's just read the proof. We reduce sorting to convex hull in linear time. So at this point, as mathematicians, you have really 2 choices. If you only want to use things that you've proved yourself, then this proof, which was sketched by Vanille and also Paul, shows that you can't do convex hull faster than you can sort. If you have seen this theorem that says that sorting n objects requires n log n time, or you believe the theorem, or you're willing to learn it in your next class, then these 2 things together show that you can't do convex hull faster than n log n time, but you need both parts. Okay, so this is pretty cool. It means that in our reduction theory, we had this weird Turing computability and Turing reduction. We had polynomial time reducibility, and now we have linear time reducibility. And basically the transformation function, in this case, just had to be Turing computable. In this case, it had to be polynomial time. In this case, it had to be linear time. But the framework and the set theoretic setup is exactly the same. And what's cool about this I think at this point in the class is you can see that we develop these algorithms, but we also know when to stop. We can prove that our algorithm is optimal. So that's pretty neat. We have an idea of how fast we really can do convex Hull.
I had a question about the theorem about sorting. Is that similar to the PNP where it's an unsolved thing, or is it like concretely you cannot sort faster than n log n?
There are some assumptions, but it doesn't require any unproven structural complexity conjectures. And by the way, this is a great question and a deep question that we can also address offline. So basically, the way it's set up is that if all you have in your setup is that you have n objects and you have a comparison function like less than, and the only way you can look at the objects and interrogate them is by using the less than function to check two things, a Boolean predicate, then you have to call that function a minimum of n log n times. And that's a theorem that you can prove robustly, and the proof is already on the web for you to look at. Doesn't rely on any structural complexity conjectures about P and NP. Now, there are some special cases. If I have integers and I know the minimum and the maximum one, I can do something called radix sort or various sorts like that that put things in buckets and are extremely wasteful in terms of space, but they will work. So if you tell me all your numbers are between 0 and 1,000,000, I can actually sort that in linear time. And of course, they're probabilistic algorithms too. But deterministic algorithms that can only interrogate the items by comparison with a predicate of less than can't do better than n log n time. So terrific question, but yeah, completely resolved, which is pretty neat. More questions? Finally, let me mention that our picture, which we did in set theory, has to hold in these cases, all these cases, and this is why I taught you set theory, that the reducing function from the set of all scheme expressions to the set of all scheme expressions has to take the problem we are, interested in proving, proving things about, has to take things in the circle, that's these problems to these problems, and the outside to the outside. Right? It has to have this particular structure that we talked about in each case. So the only difference between these reductions is how efficient are they? This just says some function. It could take a long time. It doesn't matter as long as it's a computable function. For NP, completeness has to be polynomial time. And for this kind of work we did here in computational geometry, this had to be linear time because we wanted to show something, distinctions between n squared and n log n algorithms. Wouldn't make any sense at all if our reducer function was taking, 2 to the n time, let alone even polynomial time. Okay. So this is pretty neat. It seems a little abstract, but the cool thing about it is it tells you when you can stop, when you've actually got an optimal algorithm. And now we have the tools to do that, which is pretty fun. Okay. More questions before I go on? Okay, and also thanks to everyone who thought about this problem and talked to me out of band to talk to the TAs. It's great that you could work on this and think about it. So I'd like to tell you a little bit about how these things, which are really mathematical computer science, are used in areas like robotics, and how we can extend them a little bit, do a little more algorithm design, but see how they're actually employed. So, what do I mean by robotics in general? So it's a very general term. I think of robotics as the science that forges an intelligent connection between perception and action. Obviously, to do this, autonomous robot has to be able to move around without colliding with things. It has to be able to execute and plan collision-free paths. In these environments, it can be complex, it can be cluttered, and they have to not hit things, be collision-free. So these are environments with geometry, and we have to be able to describe them using, say, polygons. So we have a map, map of some kind. And today we'll see how these computational geometry algorithms can be used in robotics. And in fact, these are used in robotics every day, even though they started out essentially as mathematical computer science. So let's think about these a little bit. So let me give you an example. I'd like to take an example here of having a robot that is essentially circular from the top. So this is supposed to be a circle, and here's a reference point here. And I'd like the robot to end up here, so this is our goal. And I want it to start maybe over here, like this. It's supposed to be the same size circle Here's robot, which is A at the start. Reference point in the center. And there's some obstacles here, right? Can't hit this thing here, and we can't hit this thing here. And maybe you can't really tell from looking at it whether or not you can squeeze through this narrow passage. Let's call this obstacle here B1, and this obstacle here called B2, right? So this topic is what we call motion planning. And the approach is called configuration space, or C-space. And there's some handouts on the web about this. All right. So again, suppose we have this circular robot and we have a map of the environment, which is where the boundaries of B1 and B2, these two polygons, are here. And they represent things you don't want to hit. And we want to plan a path for A, this guy here, that goes around B1 and B2 and gets to the goal, which looks like it might be possible. We're not sure we can squeeze through there. That's an interesting question. So without loss of generality, I want the reference point of this to be the center here, and call this point R, for example. So the trick here, as usual, is kind of representation. So basically, problems in AI typically have two components. The first is characterizing the constraints in a good representation that you can compute upon. And the second is to find a solution by search that satisfies the constraints. So this is called the configuration space transformation. Or C-space. And it was invented by Tomás Lozano y Perez. And it works like this. What we imagine doing is taking the robot A and shrinking it to a point, and then correspondingly inflating all the obstacles by the shape of A. So what we do is we take the problem of navigating just the reference point, just the point R here, around the inflated obstacles. So the theorem that Tomás proved is that the problem of navigating just a single point, the reference point, around the inflated obstacles is exactly equivalent to navigating the entire robot with all its shape around B1 and B2. So what does this inflation look like here? Well, what we imagine doing is we imagine taking the robot A and placing it on each of these vertices, like this. Supposed to place the reference right here like this, same size disks. And then what we do is we take the outer boundary, which actually is the convex hull. It's got these weird things that are curved, but that's okay. We get this guy here. And we do the same thing for B2, and we get something that looks like this. So at this point, we can entirely forget about the geometry of A. And all we need to do is we need to find a path for R. The path might look like this. And as we move along this path for the center, you know, it would be true that we could superimpose the whole robot there. But the claim is that if R avoids the expanded obstacles and can get to the goal, then A can follow the same path with its reference point, and it can avoid the original obstacles. And these things have names. There's a notation. This is called the configuration space obstacle for robot A due to B1. And this is called the configuration space obstacle for robot A due to B2. Right. Now, one thing that will be, I think, useful to you to consider is whether robots are really circular. So people like this because even if your robot is not circular, often it's a good approximation for the kind of things that are in university labs. So if you have a hexagonal robot, one of these, or octagonal robot like this is your actual robot A. Maybe you can approximate it by a circle, and you can do your planning like this. It's not exact, right? This is an approximation, but we can think about it. And let me just remind you that this might not be an unreasonable thing to do. I want to hark back to a video that we showed you before, and we can see if we can, look at one of these things. Do I have a example? So we'll just take a peek at this video again. Make sure I'm actually sharing my sound as well, because the sound is fun. Let's see. Yes. So let's just look at this again for a minute. I just want you, the only thing you should really be noticing here is that as we do this, we can see that the robots are more or less circular from the top.
The robot sense the object's orientation locally using rotational odometry and 8 discrete contact sensors.
So you see these things are roughly hexagonal.
Using what we call pushing tracking steps, in which
and these videos are on the course website.
Where the robot's internal torque limit is reached.
Okay.
Here we speed up the videotape by a factor.
Okay, so we've seen the video before, and I just wanted to remind you of this. Oh, I definitely don't want it to keep going, though, do I? Let's try to deal with that. All right. Okay. So let's stop that from running. So complicated. Go back to our visualizer. Okay, so remember that even in this case here, that's a pretty good case where we have an octagonal robot from the top. And what we're trying to do is approximate it with something that looks a lot like a circle. So the thing is that this isn't going to be a good approximation in general, right? Like, I mean, it might work for something like this, but you could have some kind of crazy thing. Like suppose your robot looked like this in our example. So your robot looks like this weird triangle here like this, triangle, and this is your reference point. In this case, the approximation with a circle is going to be really bad. You waste all the space. It'll be conservative. You'll never find a path that's unsafe, but there are lots of paths you will miss. And so that you will be, you'll be wondering, why don't I have an exact algorithm? So I hope you can see that the circle is a good approximation to a, something like this, which is hexagon or, a heptagon, something like that, but a poor approximation to a weird triangular robot. Now, of course, you might be thinking, I don't want to have a triangular robot. Why would anyone do a thing like that? Why would robots have weird shapes? Why would you do a thing like that? So I wanted to show you another video that you have not seen before. And this is actually also from my lab, but maybe you'll find that amusing. And in this, what I want to show you is that there are robots that have really quite unusual shapes here, and they especially arise when you're doing things that are difficult. So these are all on YouTube, and you can look at them, and this is about a minute long. This is an example of some work that my lab did a few years ago. And basically, these robots here are about 1/10 the width of a human hair. So they're actually micro robots or nano robots. And they can interact, and they can move around, and they can do different tasks. And clearly, they have a pretty weird shape here. And the weird shape is poorly approximated by a circle. And so you'd like to have an exact solution to these problems. Let's take a look at the video together. It's kind of fun. And you can see how these things move around. All right, so perhaps a slightly R-rated version, but we're all adults here and we can deal with that. So there's an example of some robots that have unusual shapes, not exactly triangles, but certainly not the weirdest things that you might have. So clearly we'd like to have something. I mean, this algorithm here.
Tommy's in front steering.
Oh my goodness, the video is still talking. It's because YouTube also automatically plays the next video. which is not at all what I want. So let's just fix that. Okay. Also from my lab, but we don't need to watch this. Okay. All right, so the key thing here is that the transformation we did with the disk, right? This is exact, right? I mean, the way this is set up is that there is a path for the disk exactly when there's a path for the reference point around the expanded objects. So how can we think about this in general? In other words, how can we compute CO A of B, this transformation, exactly and efficiently when A and B are actually polygons and not this weird disk here? So as usual, we're going to start off with a little bit of set theory, and that will give us algorithms. But the set theory doesn't go on for too long, and it's certainly not difficult for you at this point. So let's think about it. But it will be a little bit. I don't think you've seen it before, so I will take any questions at any time, as always, to think about this. So math to the rescue in order to solve this problem. So the issue here is that I want to define an exact way of computing the expanded obstacles when I have a polygon. So I have a definition. I'm going to say if B, which is an obstacle, and A are subsets of the plane, I don't care what they look like, I'm going to define this weird thing, B plus A, and this is the O plus in LaTeX, if you wanted to use it, to be the following things. Now remember that members of A and B are vectors, so I can add them. So I can write something like this. I can say B plus A such that B is in B and A is in A. So I have this strange object like this, and this is called the Minkowski sum. Named after the great Polish mathematician Minkowski, who invented four-dimensional space-time in physics. People associate that with Einstein, and Einstein used it. And Einstein was great, huge fan of Einstein. But I'm saying that he built on the work of Minkowski, who invented the idea that space-time is actually four-dimensional and monotonic in the time dimension. And he used this for those constructions. Very important in physics. Now I need a technical thing. I want to be able to take something and sort of invert it. Let me show you this construction. I want to be able to say big minus A, this is O minus. Remember, A is just a bunch of points in the plane. I can flip it around the origin like this for A in A. And then I just need a little notation, definition. If I take something and I basically plus it with a minus thing like this, what is that equal to? Well, I'll notate that as B just minus A. And this is simply equal to the set of minuses, the vector minuses. So B minus A, sorry, this is A, B minus A, such that B and A are in the Cartesian product B cross A. Let me just write that again to make it really clear. B minus A, such that B and A are in the Cartesian product B cross A. Okay, now this is going to be the basis for our configuration space transformation. But there's one thing we have to do, as we did before, is consider a polygon B. This has an uncountable number of points in it, right? So how are we going to do any kind of computation on something that's so big it has all these points in the interior? So as usual, this set B is in the plane, but we're going to get a handle on this guy by his vertices. So if the vertices here are 0, 0, and 4, 0, and 3, 4, and 0, 3, we can just look at the definition of this as vertices. We'll say the vertices of the polygon B are just equal to a nice scheme list, 0, 0, 4, 0, 3, 4, and 0, 3. Of course, we should probably make these cyclic to be well-formed. So I have to cycle around. So all polygons are well-formed polygons in what I'm doing here. Okay, so we now have done really an amazing thing, although since you're computer scientists, it will seem like something you do every day. We've taken a problem that is intrinsically infinite, representing the entire interior of this weird polygon obstacle B, and we've represented it in a finite way, so a computer can operate on it really by the vertices. And by the way, this guy here is often called the Minkowski difference. Okay, so we need these definitions, but let's think about how we're going to actually use these things. Okay. Now, given these, I can actually define what the exact configuration space transform is for two polygons. And I'll illustrate these, of course. So given these, I can define CO, like the configuration space obstacle for moving robot A due to obstacle B. It's simply the Minkowski difference. So it's simply B minus A such that B is in B and A is in A, which of course is just equal to B minus A, as I had before. Let me write that again in case it's not clear. B minus A such that B is in B and A is in A. So it turns out the Minkowski difference is the beast that we're going to want here. And again, because these sets could be infinite, we have to represent them by their vertices. So this doesn't help us yet because we haven't really got a way to compute this in a finite way. So the little theorem that Tomas proved was that configuration space obstacle due to moving robot A for obstacle B is actually equal to the convex hull of the vertices of B and then Minkowski sum with the vertices, Minkowski difference of minus A. And that's just equal to the convex hull of the vertices of B, Minkowski difference here, vertices of A. Okay. So let's try to think about what we would do here. So the first thing we do, we want to actually prove that this is correct, and then ask how fast we compute this beast. So let me first try to argue something about how fast we could get at these beasts here. So let's do complexity first, and then we'll try to see why this makes sense for robotics. Because right now it's just sets, right? So suppose we have the following scenario. I'll slide this a little bit. Suppose we have something like this. Suppose we have a scenario where the size of B is equal to n, and the size of A is equal to m, which is kind of a nice place to be. Now, as you can see from this definition here, where we have the cross product, the size of these sets is going to be the size of the cross product of A and B. So the number of elements in B times the number of elements in A. And saying that specifically here, we're interested in how big this set is here. We can say that if we look at the vertices of B, Minkowski difference with the vertices of A, this set here is going to be size n times m. So now we basically have an algorithm. We have an illustrated EF, we have an algorithm, right? What we do is we take the vertices of B, which is a set of size n. We take the vertices of A, that's a set of size m. Then we compute this Minkowski difference, which is basically taking the cross product and subtracting pairs in it. So now we take convex hull. So how do we understand how fast it is to do this computation? So suppose I had convex hull of a set of points V that's arbitrary. And suppose I have the number of points V equal to big N. Then the running time of this algorithm is what? Anyone want to help me out? Just for this problem here. How fast can I compute convex hull of an arbitrary set of points in the plane V if that number is N?
And log n.
And log n, big N log n. So in our case here, what is big N equal to? Like, what is the size of this set here, which I'm feeding to convex hull? Any ideas? Well, up here, we said it was n times n. So let's go with that. And that means that this algorithm here runs in time order mn log mn. Not too bad. So at this point, it will be helpful to illustrate this to see that this really works. So right now we have a bunch of things we did on sets. So we defined these sets in various ways. We have this Minkowski difference. I defined the configuration space obstacle using the Minkowski difference. And because it's a convex hull, we can compute it efficiently. But why is it good for robotics? So let me try to do that for you, and we'll come back to this. So let's go back to our example here where we had B1 and B2. And let's just do B. Here we have our robot A. A robot A, a reference point, this is polygon B1. And we want to compute configuration space obstacle from robot A due to B1. And we'll compute that as convex hull of the vertices of B1, Minkowski difference, the vertices of A. And we've just proven we can do this efficiently in nm log nm time. So the way that you would do this, or illustrate it, is we take A and first we compute minus A. So we just flip it around the origin here and we get a thing that looks like this. So given A, this creature over here is minus A. And to imagine computing the convex hull, it's a lot like what we did before by hand when we did a circular robot. So we're going to take the robot and place it on each vertex and then put a rubber band around the outside. So what does that look like? It looks like something like this. So what I'll do here in black pen is I'll take minus A and I'll stick it at each vertex. And then I'll put a rubber band around the outside, which is the convex hull, and that looks like this. And this thing here is the convex hull for A due to B. And so the amazing theorem that Tomas proved is that moving this strangely shaped robot A to a goal that avoids the polygon B1, this rectangle, is equivalent to finding a path for just a single point that avoids the expanded obstacle, which has now been exactly computed. And in fact, this works even if you have multiple things. So here I had my second polygon B2 as before, like this. So I could do this again. This is B2. And then I can also compute the configuration space obstacle for A due to B2. That'll look something like this by a similar construction. Right, this thing here is the configuration space obstacle for robot A due to B2. So in some sense, what the algorithm will do, it does this transformation, and then it deletes all the unnecessary geometry. So we only keep this reference point here and the things in red. All the things in blue and black get deleted, and to plan a path for this complicated, strange robot here, we just plan a path for R like this, and then at any point, we can imagine visualizing this by attaching the robot to it, and indeed the robot doesn't collide with anything. So the theorem here is that the problem of finding a path for robot A that avoids obstacles B1 and B2 is transformed or equivalent to the problem of finding a path for just the reference point around the expanded obstacles, which are called configuration space obstacles. And you can find a path for one exactly when you can find a path for the other one. Okay, so that's our first algorithm using convex hull. It's used practically daily in robotics, in both industry and in academia. And it uses convex hull. Okay. Questions on our algorithm?
Does it matter where R is?
That's a really great question. So it has to be chosen consistently, but it makes no difference where it is. It can be absolutely anywhere. And as long as you're consistent in how you use it, it's fine. So it can be chosen arbitrarily. Now, there might be some other advantages, like you might want to choose it at the center of mass or center of inertia if you're doing physics on this, because you can do physics in this space, but it makes no difference at all. So in fact, we could have done this. It's a great exercise. Imagine you chose R more rationally at the center of mass of A, which would be something like a point like this. Everything would still work out. Would you like to see that by choosing it at the middle instead?
Yeah, sure.
Sure. Okay. So I'm just going to, I'll do this in an inset here. So suppose we had A like this, and I choose the reference point here to be like that instead. And I have B1. So in this case here, I'm going to get a flipped A. This is A, right? So the flipped version is going to look something like this. So this becomes minus A, right? So I put minus A on all these things. So it'll look something like this. Let's see. Yeah. Not drawing exactly, but you get the idea. So I put minus A on all the vertices. And then what I do is I take the convex hull of all these points. Remember, I'm just taking convex hull of these vertices, so it's still combinatorially discrete. And I'm going to get a thing that looks like this instead. So now you see the sensitivity to the choice of reference point. So given this reference point here, which I'll call R prime, navigating R prime around this expanded obstacle is equivalent to navigating A around the original obstacle here, B2, right? But it wouldn't be equivalent if you did the configuration space transformation wrong. So you could pick a different reference point, but you get a different shape, and then you have to stick with it for path planning. Great question, by the way. Thank you.
Okay, makes sense. Thank you.
Sure. Other questions?
Yeah. So in the first example, sorry, the example above, the one that you just did, you have sort of half the figure drawn, but not the other half. And I guess that sort of makes sense because we're traversing the figure in this specific path through the middle, if that's the justification. But if I wanted to go maybe over and around, would we then have to draw the entire figure, or why exactly do you choose to draw half the figure?
Why do you think I only drew half the figure?
Probably because it seems like you're trying to go through the middle, and at that point, the top doesn't really make much of a difference, I believe.
No, I don't know. Let's be a little more specific. By figure, do you mean the boundary of the configuration space obstacle? Because it's complete. I claim I've drawn all of it.
I think my question was more about, you have A right here, which is sort of two triangles.
No, A is one triangle. I've just flipped it over for the computation.
Oh, my bad. Okay.
Yeah. No. Very reasonable point. I totally see what you're saying. A is this thing here. Minus A is this thing here.
Okay.
So the robot is
All
this
right.
triangle. It's great.
That makes sense. All right.
That
Thank
definitely
you.
could have been confusing. Thank you for asking. I'm glad you disambiguated that. More questions? All right. So to make this work, we have to stick with, we really have to stick with polygons that are well-formed, right? That's a crucial part of this construction, which is totally fine. Now, what I wanted to do next is, work with you a little bit on how we could even come up with a faster algorithm. Like mn log mn, that's basically, if you imagined a situation where you had essentially, a similar number of points in A and B, that would essentially be quadratic time times a log factor, right? You might want to do a bit better than that. So can we do any better? So that was the genius of Tomas's algorithm, is that he first came up with this, but then he asked, can we do better? So remember this algorithm here, and we proved this here. This algorithm we talked about here, this is mn log mn time. But an optimal time algorithm would only look at the size of the input. And so we want to ask, can we actually do this faster in n plus m time? And this is not a trivial question. We already saw that you can't compute convex hull faster. You can't compute that in linear time. So now that we're newly minted discrete mathematicians, having completed this course practically, and you've proven that you can't do convex hull faster than linear time, the question, can we do this configuration space transformation or Minkowski difference, can we do this faster, is a question that implies, is there an answer that doesn't actually involve convex hull? Because you can't use convex hull because you can't speed it up, because you get a contradiction. And in fact, he found a way to do this. And I want to hint at how this would work and then let you think about it a little bit. So let's set up our problem again, like this. And I think the way I want to do this is by annotating this picture here. No, I think that'd be too messy. I think I will draw it again. So remember, we have well-formed polygons like B1, and they go around in cyclic order. So I could attach geometric information to these in linear time. And one of those things I could do is attach what we call face normals. So normal is a unit vector, and these are perpendicular to each edge like this. And so imagine I compute these, I could compute these in linear time, and then each edge has a pointer to its normal, right? That's a useful construction. And I can do the same for my robot. I'll put the reference point back here, like that, and here's a reference point. I can attach normals here like this. So here's a normal, a normal, and a normal. And I hope that you can see by using a little bit of vector operations, I can compute these normals. Everything's cyclic, right? Well-formed polygons. So for B1, I can just annotate this, adding a pointer, adding a field, where I have these normals attached. So robot has normals, B1 has normals, and of course I can do that for minus A as well. So minus A looks like this, and I flip the normals over, and I have normals that look like this. Normals, normals, normals like this, all orthogonal, right? So I can compute each of these in constant time per edge, which is great. Now, the thing is, a well-formed polygon is always, vertices are in cyclic order. That's great. And furthermore, as you go around a convex polygon, the normals have to always be increasing until you get back to the origin, right? You're always going to increase, like here we go from 0 to 90 to 180 to 270 back to 360, right? They're always going to cycle around like this. And this cyclic order is actually going to give us an algorithm. Because if you look at the configuration space obstacle here, I'll draw it for you. So the configuration space obstacle for A due to B looks like this. And the thing that you'll notice about this configuration space obstacle is that every edge of CO A due to B is a displaced edge either of B1 or minus A. Let's make sure we understand how that works. So looking at our example here, every edge of this red outer boundary, which is CO due to A of B1, is either a displaced edge of B, might not be displaced at all, but it could be displaced, like this one, this one, this one, and this one, or it's a displaced edge of minus A, like this one, and this one here. And we can see that happening here too. Again, this is CO due to of A of B1, and we can see that as we go around here, we have an edge of B1 minus A, B1 minus A, B1 minus A, B1. They won't always alternate, but that's generally what will happen. Now, for every convex polygon, the normals increase monotonically and cycle around. And in fact, here, because it's a displaced edge, the normals are the same as they were before. So I have all these normals here that are from the displaced edge. So when you displace an edge, you displace the normal as well. So I have this normal, these are all these normals to these things. So this is a property of convex polygons, the normals cycle around. And so this suggests an algorithm that will be faster. And the way that algorithm can work would be as follows. compute all these normals, attach them to the edges, and then we have two input sets like this. These are the normals to B1, right? And these are the normals to B2. I'll put them in a coordinate system. So the normals to minus A. Normals to minus A, look over here, they look something like this. I got a normal like this, a little more complicated. I've got one down here, and I've got one down here like this. So these are B1 normals. This is minus A normals. And look what happens here. Here the normals cycle around because it's convex. Here the normals cycle around because it's convex. Here the normals cycle around because it's convex. So this is our second two-finger algorithm. What I do is I go through this list and I merge them in linear time. Again, there are n of these and m of these. And so in order, look what happens here. I'm going to start with this normal here, and I'm going to just look at a back pointer to find out what edge it is. Well, what edge is it? It's that edge. So I put an edge there for my polygon. Now I'm going to cycle around counterclockwise, and I'm going to take an edge of B or an edge of minus A, whichever I encounter first. So coming around like this, I now encounter an edge of minus A. I go to this edge here. I find the normal, and I put in the edge. Continuing around in doing this, I now am going to find this edge here. So the way to think about this is that I merge these edges into a single list in linear time. And that merged list will look like this. Here are the normals of B1. Here are the normals of minus A. Like that. So again, cycling around, start here, get that edge, put it in the configuration space obstacle, come around here, counterclockwise. Now I have a normal that's red of minus A, take that edge, I put it in, I get this edge here, come around here, now I have an edge of B1, that's this edge here, I put that in, cycle around to this guy, that's a, look at the back pointer, that's an edge of minus A, it's this edge here, I put that one in. Now I come to the next one, which is this guy here, that's this edge here of B1, I put that one in. Finally, I come over here, I have an edge, which is this one of minus A, put that one in. And so since I have n of these and m of these, my two-finger algorithm just comes through and I can merge these in linear time, and then I can have the optimal algorithm is order n plus m. So by exploiting some of the basic mathematical properties of these, we basically used a two-finger algorithm to merge two sorted lists, a problem that can happen lots of places. We can represent sets this way. You saw this on one of the midterms, I think. And basically you traverse the orientation by taking the next orientation from both lists and create a merged list in linear time, n plus m. And this gives the order to the edges in the configuration space obstacle for robot A due to B. The displacement can be just calculated from the last edge. And this gets you going. So this means that there's a theorem that you can compute the configuration space obstacle for obstacle B for robot A in linear time, which is really quite a remarkable thing. So I wanted to point this out, and I wanted to mention some challenges for you to think about. So first of all, I've made some assertions here. You would want to prove them. Like, how do you know these things are true? And second, what I wanted to mention is, before when we tried to do faster convex hull, we had a lower bound that we proved using reductions that you couldn't do it. Here I'm doing something similar. I am abandoning convex hull, but how do we know that this doesn't violate some other property? And essentially the reason you should look at is that because I'm not using convex hull, the argument that convex hull can't be faster than n log n doesn't apply here. I'm not using convex hull in any way except mathematically. So I'm using the property of convex objects, but I'm not using a convex hull algorithm in some sense. So what you should verify for yourselves is that this really is a linear time algorithm and that it's sound, but also that I haven't violated any properties that would be unfortunate. Like I haven't done anything like proved an algorithm that can't exist. So in other words, with convex hull, we had a proof by contradiction essentially that you can't go faster than n log n. In this case, I'm claiming that we can go faster because we're abandoning the convex hull algorithm, but you want to make sure that claim is really true. Okay. So this is in the notes and you can look at it and it will be covered in future classes, but I wanted to give you a peek at how we use algorithms complexity, geometry, and sets to do things in the real world, such as robotics. So at this point, what I'd like to do is kind of just summarize and philosophize for just a few minutes as we kind of wrap up our lecture here. And I kind of made the summary slide of the last few lectures. And we were able to cover a lot of things. So we talked about having good representation, so we could make algorithms such circular lists, fast algorithms for making our procedures safe even when you have circular lists. And we talked about adding some assumptions to the objects we're computing with, which we call in mathematics regularity. Like we might have convex objects or objects that are well-formed polygons. The very common thing in mathematics is to try to restrict the class of things you're looking at initially to things that are well-behaved. And then, of course, we looked at algorithm design, time and space complexity, not only for circular lists, but for convex hull. And we've got some interesting things happening. We found gift wrapping, which only works in 2D and is quadratic, divide and conquer, which works in 2D and in 3D, gram scan, which only works in 2D. This leads to some math problems. Like, for example, you should be maybe thinking of a math class in the future where you might ask, does divide and conquer actually work in 4D? And that's a fascinating question that we can do in a later class, but beyond the scope of this class. We also looked at optimality. Can you prove that you're done? You have the fastest algorithm that's possible. Well, yes, using reductions, using, in fact, linear time reductions, we can reduce sort to convex hull and show that n log n is actually optimal. And we did that. And in fact, in order to do some of this work, we had to use a variety of complexity models, even amortized complexity for gram scan, which you'll see in later classes. Now, finally, we looked at some applications like robotics and motion planning, and even sketched how to come up with an optimal linear time algorithm, but we're rather careful about coming up with an algorithm that used convex hull. One kind of interesting thing about this is the optimal linear time algorithm only works in 2 dimensions, right? Can't work in 3 dimensions for rather deep mathematical reasons we can discuss later, but the convex hull algorithm actually will work in 2D or in 3D, even though it's a little more expensive. And of course, robots really live in 3D, so you kind of want to use that algorithm. And again, we hinted at some things you might see later, namely math to answer some of these questions. Can we add physics to this kind of geometry? In other words, we want to do more than just avoid obstacles. We might want to pick things up and deal with friction and dynamics and speed. And yes, you can add that to this model. And we need a little more math for that in a later class. But we began to go into questions involving artificial intelligence, which you saw a little bit of in problem set 3 and 6. Namely that, again, in AI, there are really 2 parts of any problem, right? We have to characterize the constraints, and we want to search for a solution to satisfy the constraints. And we began to see glimmers of how to do that. When you take an AI class, you may see more of this. So I think you're very well positioned, based on this class, to go on and take some of these classes and enjoy them. So my summary of where we are now, aside from this slide, is that in the past just 3, maybe 4 lectures, we could do really quite a lot of computer science in a few lectures. And we could do a lot because now you know really quite a lot of discrete mathematics. And I think it would be very difficult to have covered this material, especially in this depth, without the discrete mathematics that we learned to have a foundation for understanding the material. But I'm confident at this point that you could not only understand it, but you could implement it and build it out for applications in robotics, graphics, animation, biology, data science, based on what we've done. And I'm very proud of how far you all have come in learning mathematics for computer science. And I think the fact that we could cover all these topics is enabled by the math that we've studied together and tried to struggle through and trying to situate this and seeing how it relates to computer science. So what lies ahead in the future? So I think that in the future, I hope you'll continue to study mathematical computer science, and not only for its own beauty and its elegance, but also because you can efficiently and correctly design and use algorithms that are grounded in provable correctness and provable completeness, complexity, and so forth. And hopefully you can leverage some of the principles that you've mastered in this class. And that's what I've been trying to get you, not only to the foothills, but even climbing some of the first peaks of how we do that in computer science. I just wanted to thank you all and say it's been a pleasure to explore some mathematics, to get together a couple of times a week and talk about mathematics and computer science. I've really enjoyed the questions, and I hope you all have a great time learning mathematical and computer science in the future. And if you have any questions as an alum of the class, please feel free to come contact me, reach out. Even after the class, I'm happy to chat with you. And finally, thank you for being willing to take this class even remotely and during a pandemic, which is not an easy time to learn. We've all had fun working with you, and I appreciate your patience as we worked out a really new format for this and enjoyed the conversations we had. It's been a pleasure. So thanks a lot.
Thank you.
Thank you.
You're very welcome.
Thank you.
Thank you.
Thank you.
Thank you.
Yeah, thank you so much.
Thank you. Appreciate it.
Thank you.
Thanks.
Thank you all.
Thank you.
Thank you all very much. I'll be staying around for office hours in case anyone has any questions. I really appreciate your comments. I'll turn off the recording now, and I'll just stay around if you'd like to chat. I'm happy to do it. I really appreciate all your comments verbally and in the chat. Thank you so much.